So we were talking about the stereoisomers, about the double bond, because groups could either be on the same side or they could be on opposite sides, and that restriction in the rotation is the stability, the additional stability in that bond, which is going to prevent from one getting converted into another. So whenever you have groups pointing in the same direction, we call it cis. Kind of makes the s sound. We've talked about all this stuff previously as well, when we discussed our cycloalkanes. And likewise, if you wanted to consider trans, that means across. I often think about it as transatlantic call, for example, right? So here you see the double bond. Your two groups, the two methyl groups, one is on one side, the other is on the other side. We are going to use the word trans to describe that. Long story short, each carbon here must have two different groups for these isomers to occur. So here I showed you the difference between the cis-2-butene and trans-2-butene. If you were to compare and you were to say which one is more stable, hopefully you can see that trans is going to be more stable because bulkier groups are on opposite sides. Likewise, if somebody asked you which one of them is more polar, you would say that the cis is more polar because the groups are going to pull the electrons towards the same side of the double bond. They are not going to counter it, as compared to the trans molecule, in which the two groups could counter each other, and hence being directional, the polarity, the dipole moment as we see it, as is going to decrease. It's going to become zero. This slide basically highlights what we have been talking about. If you are seeking cis and trans, there must be an actual pair across the double bond. That means you have to look at the double bond, and on that double bond, on carbon number 1 and carbon number 2, there should be groups that will look same or different. So that means if you have A and B, let's say here, then there must be a B, because that's what you are comparing, right? And this would be A, and then you would say that these are trans. These are trans. But you can't have the same group, such as the one that they have written down here. They can't call that as cis or trans. So for example, if you see a double bond at a terminal, that is the first carbon that you are at, 1-butene, 1, 2, 3, 4. It cannot have a cis or trans, because when you're comparing across the double bond, you find exactly the same group, right? So when that happens, then you should not be seeking cis or trans, because you're not going to find one. So keep that in mind. So this first example that has been shown here, these are not compounds that are cis or trans isomers. They are actually identical, because on one carbon you have an A and a B, and on the adjacent carbon participating in the double bond, you have both the positions that are D. Even if you were to flip that, you will still continue to have the A and the B on the same carbon, and the two Ds are going to be on the other carbon. So that means at any given point of time, this B is opposite 1D, this A is opposite the D, B opposite to D, A opposite to D. So that nothing changes here, right? On the other hand, if you look at the bottom example, if you look at the one at the second one, essentially, here A is opposite E and B is opposite D. And when they flipped that, so when they flipped this position, let's highlight that a little bit. When they flipped this position, then they are seeing that now B is opposite E and A is opposite D. So we saw a completely difference in the molecule, in the stereochemistry, and so these are the cis and trans isomers. Now, it should be mentioned here that the cis and trans naming system that works only with di-substituted alkenes. And so what that means is that there are two substituents other than the hydrogen on the double bond. Now, sometimes alkenes could have a tri-substituted and tetra-substituted double bond. That means you have, there is a need to have a more generic way of naming things, of describing the double bond geometry. So, for instance, when I use the word tri-substituted, meaning maybe you have a double bond, maybe one of them is a hydrogen and maybe this is a hydrogen. You have a Cl here, right? And you have a CH3, and maybe this is actually a CH2 and a CH3. So all of the four positions are completely different, right? So you use the word, in this case, since only one position is hydrogen, you would use the word tri-substituted, meaning three substituents other than the hydrogen on the double bond. And you would have used the word tetra-substituted if even this was, suppose it was bromine. So all of them were completely different. You would have used the word tetra-substituted. And such compounds do exist. So there had to be a better method, a more generic method, sort of like a bigger umbrella to put the names together. And so for that reason, like I just described, the cis and trans nomenclature worked only for the di-substituted double bonds. For tri and tetra, we needed more help. And so the E and Z came into being, and that work was done by Kahn, Ingold, and Prelog. Sometimes these are also referred to as the SIP rules. Okay, so what they do is across the double bond, they would assign priority with respect to the atomic number. So what that means is that if your atomic number is high, so if atomic number is high, that would mean you have a high priority. Atomic number low means that you have a lower priority. And then they would see where the high priority groups are. If the higher priority groups are on opposite ends, that means they are across the double bond, then you're going to say that this is across, it's E, it's, I like to call it anti, or maybe anti, and it means entgegen which is German for anti. Likewise, if you had to look at the priority orders and they end up being on the same side, or did I say same side, or did I say same side, then we would call it Zusammen. So that would be Z. Does that make sense? So two words, anti and same for E or Z, which will allow you to give a broader picture or get a broader picture of nomenclature, of designating certain bonds in a specific manner. Just couple rules to get you guys thinking about it. When you're comparing, you must rank atoms at the comparison point. That means you start when you're looking at the two groups across the double bond. So I like to look at groups across the double bond, and they must be what you're comparing. They should be on the same side of the double bond, right? That's why I put a vertical line here. But these are the two groups that you're comparing. So the point of attachment is this carbon. So I'm not going to compare the methyl group, but rather the carbon atom. And I'm going to compare that to hydrogen. Because remember, atomic numbers are for atoms, not for CH3, right? So I'm comparing carbon to hydrogen. So hydrogen being atomic number Z of 1 and carbon being at 6, carbon gets priority. And if you look at what you have on the other side, you have Cl versus carbon. So carbon gets the lower priority, Cl wins. My high priority groups are on opposite sides of my double bond, and so I would call this an E isomer. So notice in my nomenclature, I'm no longer calling this just 2-chloro-2-butene. I'm going to call it E2-chloro-2-butene. Depending on the number, sometimes you would also see this written as 2E because that specifies the position of the double bond. Now, in this particular case, it won't matter because there's only one double bond. So writing it as E2-chloro-2-butene is just fine. But if you have a diene or a triene, then calling that 2E, 4Z, etc., as the case may be, would have to be done. So basically, you would be providing the location of the double bond and the E or Z pattern on it. And we'll take some examples as we go. Let's take a look at the second one. Again, it's the same groups, but the positions are different. So basically we flipped our CH3 and the Cl such that both the high priority groups, they became on the same side, and so since it's the same side, we are calling it a Z2-chloro-2-butene. So what you're looking at is the two isomers. We are going to call these constitutional isomers. You can also call it geometric isomers. So two names for that, constitutional or geometric isomers. The next rule is suggesting that if the atomic numbers are the same, then we go to the next atom, provided the next connection that you have is being compared at the same distance from the double bond. So what that means is that if you have, let's say, a double bond, and you had a CH2, CH3, and you had a CH3, and maybe here you had a Cl and you had a Br, and I'm going to put a, and so we have to compare Cl to Br. Of course, bromine has the higher priority, so because it has a higher atomic number, so I'm going to give that a high score or a high priority. Between CH2, CH3 and CH3, notice that the CH3 is nothing but a CH2 connected to another hydrogen, right? That's what it is. Just like this is a CH2, you have a carbon connected to CH3, and you can open it up if you want to be able to see what I'm talking about. That's the CH2, CH3. I'm going to do the same thing over here, just so you are able to follow along what I'm trying to tell you. So I have a carbon, which is a CH2, and then there is a hydrogen, right? So I'm going to now highlight what are my two groups. My two groups are, oh, I found a carbon to another carbon. So what do? We go to the next element. So the next element that I found here was hydrogen. The next element I found here was a carbon. Who's the winner? Carbon. Good job. And so you're going to find high priority up top and low priority with the methyl. Where are your high priority groups? On opposite sides. So this must be E. Does that make sense? Okay, great. Let's go to the next one real quick. And that says that if you have multiple bonds, so if you have a C double bond O, then that should be counted twice. The oxygens will be counted twice. Okay, so that's pretty simplified to read through. We are going to just now apply this onto some molecules and see if we can determine, if we can assign the E and Z. So let's take a closer look at what we have. So over here I have some molecules and we have to assign E or Z configurations. So let's take it one by one. One of the things, like we discussed, we have to compare the groups on the same side. So I'm going to do the same side vertically, but it's across, right? So I always think about the double bond as if it's a river or a road, and I am standing here, and here is one of my children is there, and I'm looking at them, and we are, that's what you want to compare. So just on the same side, vertically, but across the double bond. So I'm comparing my C to my C of the CH2, CH3. You find the same carbon. What do? You move to the next atom. If you really want to, you can totally just pause me here and just compare after the discussion whether it matches, or you can let it play however you feel like. But hopefully you can see that this is going to be your high priority. This is going to be your low priority. I'm going to do the same thing on the other side. So we have a Cl that's going to now be compared to the carbon. So Cl receives higher priority. This receives low priority. Both the high priority groups are on the same side. It must be a Z. Let's take a look at the next one now. Again, you're going to go through your molecule, compare your methyl with the hydrogen. So that's your high priority. When you have the C triple bond N, so don't forget that there is a triple bond. That means that you have to draw that out. You have to write it out 3 times as single bonds. For CH2, NH2, you will write it as CH2 and NH2. So now when you're comparing, you're first comparing the carbon against the carbon. You go to the next element. Here I find hydrogen, hydrogen, 1 nitrogen. Here I find nitrogen, nitrogen, 1, and the third nitrogen as well. That means who's the winner? Who's the high priority? The CN is the high priority. So your high priorities are on opposite sides. This must be a E molecule. Let's go forward with the third one. I have over here, I'm comparing a Cl to an oxygen. Who's the winner per the atomic number? The Cl that's at 17 as against oxygen, which is at 8. So your high priority group is chlorine. And for the ethyl versus the propyl, we are going to go atom by atom. So that's a carbon against carbon. What do? It's a CH2. We go to the next one. I find another carbon and another carbon. This carbon is going to 2 H's and a third H. This carbon is going to 2 H's and the third C, right? So you're basically comparing your carbon versus a hydrogen. And so for that matter, for that reason, the high priority group will be the propyl group as compared to the ethyl group, which is why you would say that this is going to be an E molecule as well. Let's go ahead and take a look at the next molecule. We have the double bond. We have the COOH. So I'm going to just spread that out as what it might look like. The 2 hydrogens and a single oxygen. Here you have 3 oxygens. Hopefully you can see that that's your high priority group. Here I found CH2 against CH2. Here I go to the next one. This is a CH2. That is a CH going to a CH3. So the high priority is up here. Sounds like both the high priority groups are on the same side. So this must be a Z molecule.